Hello everyone, in this video I will be explaining the physics behind collisions between circular objects. Now this video is going to be quite physics heavy, so I hope you have an understanding of basic motion and some physics, but not too much because all the concepts that we need I will explain as the video progresses. So I intend for this to be a prerequisite to a future video where I show you how to actually code up one of these simulations. So if you don't want to miss that one, make sure to hit that red subscribe button. Alright, without further ado, let's get straight into the video. So there's a few things we need to know, and one of them is called Newton's laws of motion. Okay, so you may or may not have heard of these before, but here they are as we are going to use them. So the first law states that objects maintain their velocity if there are no outside forces acting on them. So for example, a rock hurtling through space at like 10 kilometers per hour, or 10 meters, 10 kilometers per hour, would continue traveling at that speed if there's no gravity or anything else acting on it. We're not actually going to use that one that much. It's kind of nice to know though. Now, law 2 is going to be F equals ma. This states that the force on an object is equal to its mass times its acceleration. And then law 3 states that every force has an equal and opposite force. So in our collisions, there's going to be two balls colliding, and if there's a force exerted on ball A that's in this direction, then there's going to be an equal and opposite force exerted on ball B. Alright, so those are Newton's three laws of motion, and now let's just get into the collisions. So we will be tackling one dimension before we go on to two dimensions, because the two-dimensional case will highly utilize the one-dimensional case, and it'll just lay out some of the concepts we need to know beforehand. So let's say there's two balls, they're in the same axis because it's, one dimension. The first ball has mass m1, second ball has mass m2. First ball is traveling at a velocity of v1, and ball 2 is traveling at a velocity of v2. So, what do we want to figure out? Well, we want to know the final velocities of these two balls, right? That's our goal. Our goal is to find v1 prime and v2 prime, where these are the final velocities of the two balls. So let's lay out what we know in a nice grid or table. We have our knowns and we have our unknowns. What we know is m1, m2, v1, and v2. We also know this extra parameter called e. This is called the coefficient of restitution. And this I'll explain later on, but basically we have five knowns. And we have two unknowns, v1 prime and v2 prime. So we're actually going to find these unknowns in a bit of a convoluted way. We're actually going to find v1 prime, and then using that, we're going to get the force exerted on ball 1. And this is automatically going to give us the force on ball 2 because of Newton's third law. Every action has an equal and opposite reaction. So the force on ball 2 is going to equal the negative of force on ball 1. And I should clarify, if you're not familiar with what force is here, technically it's impulse, if you want to be really specific, but basically force is just a measure of how the motion of the ball is going to change. And specifically, force is equal to ma, right? So the force on ball 1 as a result of this collision is going to equal to the mass of ball 1 times its acceleration. And the acceleration is really what we're looking for, because the acceleration just represents the final velocity minus the initial velocity, or how much the velocity changed. Now for ball 2, the force on ball 2, same thing, equals m2 times a2, where a2 is going to be equal to, I just realized you can't see any of this because my face is blocking it. Okay. Where a2 is equal to v2 prime minus v2. So we're going to do this in a convoluted way. We're going to find the force on ball 1. We're going to find this. And from that, we'll extrapolate the acceleration on both balls as a result of the collision, and then we will compute their final velocities. Okay, but how do we actually do that? Well, we're going to use equations. Don't be scared. There's only going to be two equations, and they're not that complicated. Okay, number one is called conservation of momentum. Now, what this states is that momentum is conserved in the system before and after the collision. But what does that mean actually? Okay, well, momentum is equal to an object's mass times its velocity. So the total momentum is preserved as a result of the collision. So total momentum, what's that going to be? Well, before, it's going to be equal to m1 times v1, this is the momentum of ball 1, plus m2 times v2, which is the momentum of ball 2. And the momentum after is going to be m1 times v1 prime plus m2 times v2 prime. So that's our equation. If you want to see why this is true, or at least an intuitive explanation for this, you can look at the center of mass, sort of, and total momentum represents the momentum of the center of mass. Specifically, it's going to be the combined mass times the velocity of the center of mass. So if you think about in a collision, the center of mass is not really going to change as a result of the collision. There's a more rigorous way to do this, but that's how you think of it. All right, and now our second equation is called restitution. Now, restitution has to do with the relative speed, the change in the relative speed as a result of the collision. So we have a before and we have an after. So before, let's say, for example, balls are heading towards each other at 10 meters per second. And v2 is going to be negative 10 meters per second because it's heading in the opposite direction. So if we look at ball 1 and we think we're ball 1, right, just imagine, then ball 2 is headed towards us at 20 meters per second, right? So that's going to be 10 meters per second minus negative 10 meters per second, which is going to be equal to 20 meters per second. And say afterwards, maybe, you know, it's a non-bouncy collision. Inelastic is the correct term, I believe. Then maybe they're headed apart at 9 meters per second. So the relative speed would be negative 18 meters per second. And the change in this would be 0.9. So our coefficient of restitution would be 0.9. Now, there's no law in physics that, you know, describes the restitution of a collision, but this is just a way for us to parameterize the bounciness of the collision. So if you can think of, for example, if the restitution was 1, the collision would be very bouncy because the relative speed would be the same. It would be like a bouncy ball hitting the ground and then bouncing up back to the same height. And if E was 0, then you can imagine two very maybe heavy non-bouncy objects. After they collide, they just kind of stick to each other and move very slowly or something. I don't know. So equals 0 equals non-bouncy. Well, equals 1 is bouncy. The correct term for this is elasticity. So equals 1 is a completely elastic and equals 0 is a completely inelastic collision. But we don't really need to worry about that. We just need to know that the coefficient of restitution is between 0 and 1. Okay, now we actually need to turn this into an equation. All right, so relative speed before is going to be equal to, let's just add on to this little table we have here. All right, so before it's going to be equal to v1 minus v2. We could do v2 minus v1, but it's the same anyway. And then afterwards, it's going to be v1 prime minus v2 prime. So what we can write is that v1 prime minus v2 prime equals negative e, where e is the coefficient of restitution, times v1 minus v2. And the reason we have a negative sign here is because the balls are headed apart afterwards. So the relative speed sort of flips signs. All right, so this is our second equation. And with that, we have our two equations. And let's just summarize that here. Our equations are, 1, the conservation of momentum, m1 times v1 plus m2 times v2 is equal to m1 v1 prime plus m2 v2 prime. And then our second equation, restitution, is going to be v1 prime minus v2 prime equals negative e times v1 minus v2. All right, now we have to solve these equations. Remember that we're only going to solve for v1 prime because what we're really after is the force as a result of this collision, and specifically the force on ball 1, and then we can extrapolate the force on ball 2. So I'm probably just going to do a time-lapse algebra thing here. It's not too complicated, but I will spare you the calculations. Okay, brilliant. We have our equation. We know what v1 prime is. Now, admittedly, this is a bit complicated, but we won't have to do this by hand usually because, this is for coding up a simulation. So we don't care that it's complicated. The computer will handle it just fine. All right, and now, as promised, we will find the force as a result of the collision. Okay, the force on ball 1, recall that force on ball 1 equals the mass of ball 1 times the acceleration as a result of the collision on ball 1. And the acceleration of the collision is just v1 prime minus v1. So now we have the force of the collision on ball 1, and now we need the force of the collision on ball 2. So that's going to be equal to negative f1 because of Newton's third law. So that's going to be equal to m1 times v1 prime minus v1. But this is also equal to m2 times a2. Expanding this out, we get m1 times v1 prime minus v1 is m2 times a2. So a2 is just going to be m1 over m2 times v1 prime minus v1. All right. And we could even shorten this down to a1. So a2 is equal to m1 over m2 times a1. And intuitively, this makes sense because, you know, if m2 is really heavy, then the acceleration on ball 2 is going to be pretty small, so this denominator is going to, you know, really reduce the term down. Whereas if a2 is really light, then m1 is going to win out, and then ball 2 is just going to accelerate a lot more. So now we have our equations for acceleration 1 and acceleration 2 derived from the force of the collision. So yeah, you may be wondering why exactly we're computing the force and the acceleration on the two balls as a result of the collision instead of just directly computing v1 prime and v2 prime. And the reason for that is when we get up to 2 dimensions, it's going to be a lot more convenient for us to compute the force and then the acceleration instead of directly computing v1 prime and v2 prime. All right, now let's move on to 2 dimensions. This is what we've all been waiting for. All right, 2 dimensions is actually not that different from 1 dimension. It does require a little bit more thinking, perhaps, but overall it's not too complicated. So we got these 2 balls, right? They may be colliding at an angle, so not perfectly as in 1 dimension. But we're going to define 2 lines here. This one we're going to be calling the plane of collision. The reason it's called a plane is actually because in 3 dimensions you actually do get a plane, but in 2 dimensions we just get a line. And then over here we're going to call this the normal axis. And we call it this because normal in physics means perpendicular. It also means perpendicular in math. So this is just going to be the normal axis to the plane of collision. All right, and let's say again that our balls have mass m1 and m2, and that their initial velocities are v1 and v2. And now notice that the velocities are actually vectors now. They have both a speed and a direction instead of just being a number in the 1-dimensional case. How are we going to reduce this down to the 1-dimensional case? Well, if you'll see, the force exerted as a result of this collision on either ball is only going to occur on the normal axis. And if you think about why this is true, if you zoom in really, really close, you're going to get something like this, where they just look like flat lines. And obviously then it's only going to be exerted in this direction because it's symmetrical in either way. And further, if you think about it as 2 bricks or flat surfaces colliding, then obviously the forces are only going to be exerted in the normal axis. So what does this mean? It means that we only care about motion in the normal axis because that's going to be determining the force. So if we have ball 1 here and the normal axis here and its velocity is just here, then we only need to care about the component of the velocity in the direction of the normal axis. And if you're familiar with what component means, then cool. If you're not, then it basically, if you have a vector, you can decompose it sort of into 2 subvectors that add up to the original vector and which are perpendicular. So if you rotate it a certain way, it kind of looks like the x-coordinate and y-coordinate. So that's basically a way to think about it. So if we take both the velocities of the 2 balls and we project them onto the normal axis, then we will get the only component of velocity that we actually care about, because that's where all the motion is happening. Specifically, how we get this is if the normal plane is represented by this vector, maybe like d or something, and it's a unit vector, so it has length 1, then we can do v1 dot d times d. This is the length of the projected vector of v1 onto d. This is called the dot product, and if you're familiar with that, this should make sense, but if you don't, this is basically a definition of the dot product. You're projecting something or finding a component of a velocity or vector in the direction of another vector. And the dot product actually returns a scalar, so we multiply that by d to get an actual vector that we can work with. Okay, actually it turns out I'm wrong. We don't have to multiply by d, we only need the scalar. Yeah, okay, we've got this normal axis. We're going to rotate it so that we can see it more clearly. So now ball 1 has this velocity going in this direction. We can do the same for ball 2 so that its velocity is going here. So if we denote it as maybe like v1d or v1n, maybe that's more appropriate, v1n and v2n as the velocities of the two balls, then we have a one-dimensional problem. And recall, this is because all the action is going on in the normal axis. We don't have to care about motion in any other axis. So that's why we project it onto this normal axis. And now we have a one-dimensional problem, right? So we can compute v1n final and v2n final. So the velocity of the balls in the normal axis after the collision. But this doesn't give us the full picture yet. We need the full velocities, not just the component of velocity in the normal axis. So this is where the convoluted thing we did in one dimension pays off. We find the force as a result of the collision, and specifically the acceleration. So the acceleration on ball 1 is equal to v1 prime n minus v1 n. Because remember, acceleration only occurs in the normal axis. And then acceleration of 2 is just equal to m1 over m2 times v1 n prime n minus v1 n. Recall, as we did in the earlier computation over here. So yeah, we have the acceleration of the two balls as a result of the collision, only in the normal axis again. So we can do v1 plus a1, and then v2 plus a2. Actually, before we do that, we actually have to multiply these by d, because again, these are scalars, because in the one-dimensional case, we were also working with scalars. So the acceleration is going to be returned as a scalar. We can multiply that by d to get an actual vector, which is going to be in the normal axis. That's why we multiply by d. And recall d is a unit vector, so that's why we can do this. And then the acceleration on ball 2 is going to be a2 times d. All right, now we have our acceleration on the two balls as a result of the collision. Now we can do v1 final equals v1 plus the acceleration on ball 1, and the final velocity of ball 2 is equal to v2 plus a2. And that's pretty much it for 2 dimensions. To summarize what we did here, we drew a plane of collision, which actually we didn't really use that much, and we drew a normal axis. We figured out that the only action going on is in the normal axis because the force exerted as a result of the collision is only in the normal axis. And then we projected the vectors onto this normal axis because the only component of velocity we care about is in the direction of the normal axis. And we did that by taking a dot product with a unit vector that represents the normal axis. After that, we have v1n and v2n, which are scalars, and they represent the components of the velocities in the normal axis. After that, we just do a one-dimensional collision, as we explained up here, and that gives us the acceleration of the two balls, only in the normal axis though, so we do have to multiply by d to get the full vector that represents acceleration. After that, we just add them on to the velocities, because that's the definition of how acceleration works. And we have our final velocities for the two balls. We can reassign them, and then we are done. Great, that is the bulk of the video done. You now know how to compute the final velocities of the two balls as a result of the collision in 2 dimensions. Or we could carry this on to 3 dimensions, but it's more of the same thing. The normal axis is still just an axis, it's just a line. Actually, all of this carries over. But we're just going to leave it for 2 dimensions because it's the same for higher dimensions. All right, and now there are a few things we didn't cover, but which are going to be important to making a simulation. Number 1 is going to be collision detection. Because when we're actually going to make the simulation, we don't want to do this collision computation if these two balls aren't colliding. So 2 balls are colliding if and only if the distance between them is less than or equal to the sum of their radii. It's pretty easy to see because these are circles. That's the reason we did circles, because it's easier to do computations on them. If you see that d is less than r1 plus r2, then or equal to, then they're colliding. All right, number 2 is actually very important. If these balls are already heading away from each other at the moment of collision, then we don't want to do any collision computation. So you can imagine 2 balls already pulling apart, then you don't want to do any computation because that's going to cause a few glitches, and they're moving apart anyway. How we actually find this out is, and actually it's probably easier to see this in the one-dimensional case and then just carry it up. If you subtract the 2 velocities, so if you look at the relative speed, and the relative speed is a negative number, then you don't want to do a collision. So for example, if we had 1 meters per second for ball 1 and 10 meters per second for ball 2, and they're pulling apart, relative velocity would be negative 9 meters per second, so you don't want to do any collision computation. On the other hand, if it was something like 1 meters per second and maybe like negative 1 meter per second or even like 0.5 meters per second, then you would do a computation because they're going to end up colliding. Carrying this up to 2 dimensions is easy. We just do the same projecting stuff that we did. All right, third is not important, but if you have two balls and they're intersecting, then we actually have a way to pull them apart based on their mass. Very useful if you have two balls that start out colliding. It makes it a bit smoother and maybe a bit less glitchy. I'm not sure. But there's a way to move them so that they're not colliding anymore. I'm not going to elaborate further on this because this video is already pretty long. But I will explain this in the next video where I actually implement this. Alright, thank you very much for watching. This has been quite a difficult video to make. If you have any questions, as always, leave them down in the comments and I will try to answer. And stay tuned for my next video where I show you how to actually implement this in code. It's going to be quite the epic video. So make sure you don't miss it by hitting that red subscribe button, and I will see you next time. Goodbye.